So today's focus, we got a couple parts. Today we're going to first look at the trigonometry functions, so refreshing your memory about unit circle, graphing trig functions such as sine and cosine, and then being able to solve various trig functions. So here we have a little warm-up, refreshing your memory about using your unit circle to be able to find these. One thing you got to remember about the unit circle is that any coordinate around the unit circle, the y coordinate represents your sine, and then the x coordinate represents your cosine. And remember any reciprocals of those, right? Cosecant, that would just be the reciprocal of whatever the sine is, so 1 over y there. And then tangent, you'd have to find, if you find tangent of values, right, that's the same as taking sine over cosine. So on the unit circle, that's your y coordinate divided by your x coordinate. So in the first one, letter A, if you kind of interpret that, I guess we're trying to find at 225 degrees on the unit circle, what's the y coordinate there? And so we need to have our unit circle out, which notice here, here's the unit circle with have all the exact values around it. So this is something that you're expected to, let's say, not memorize fully, but it is good to know this, especially when you're solving trig functions or doing some calculus later on. So again, any x coordinate that represents your cosine function, whatever that angle is, and then your y coordinate represents your sine. Another thing to remember is if you're looking up inverse trig functions, such as the sine inverse, cosine inverse, or tangent inverse of a certain radian measurement, this pertains to a certain domain. And so when you're looking at the sine inverse and tangent inverse, that's specifically your right half of the unit circle. So sine inverse, tangent inverse would be right half, and then when you're looking at the cosine inverse, so anytime you're looking up cosine inverse, you're specifically looking at the top half of the unit circle only. Now one trick to remember the unit circle is what's called the hand trick. And so if you place your hand or the palm of your hand sort of in that first quadrant, that these fingers that you have line up exactly with the angle measurements, even the 0 and the 90 degree. And so if I want to find out what the coordinate is quickly at pi over 6, which is 30 degree mark, what I do is I bend this pi over 6 finger. So I bend it so it's down below now. And then what you do is the trick is the coordinate there is the square root of your fingers left. The bent finger produces the comma, and then the other one would be the square root of the other finger, and it's always over 2. Everything's always over 2 in that quadrant. And so that's just a quick check. And so if you did, like, let's say, what's the coordinate right at 45 degrees? What I do there is I quickly bend my 45 degree finger, so then now it's facing down, and then that creates the comma between the two coordinates. So I know at 45 it's the square root of 2, because that's what I have to the left of that bent finger, over 2, and then square root of 2 over 2. And so I'll show you that a little bit more tomorrow in class to help you out, but definitely know your unit circle. So if we're going back to the warm-up problem, to be able to look up what the sine of 225 degrees is, it's really what is the y coordinate at 225 degrees. And so notice 225 is down here, and the y coordinate there is negative square root 2 over 2. So my answer would be negative square root 2 over 2. In letter B, you're finding when the x coordinate at negative 5 pi over 6. One thing about the unit circle is negative angles go counterclockwise, right? So if 5 pi over 6 is sort of right here at the 150 mark, negative 5 pi over 6 would be actually ending up at the 7 pi over 6 mark, right? It's kind of a reflection of that. And here we're trying to find what the cosine is, what the x coordinate is at that coordinate, and notice the x coordinate there is negative square root 3 over 2. If we jump up to D here quickly, here we're finding the x coordinate at 570 degrees. And so if I go in 570, which is not directly on the unit circle, that's exactly once around 360 plus another 210 degrees, right? And so it looks like I end up at that same coordinate. We're trying to find the cosine, aka x coordinate, so it ends up being the same answer as letter B. Now for letter E, when you're looking up cosecant, cosecant's the reciprocal of sine. So my thought process here is let's first find what the sine of 2 pi over 3 is, which is the y coordinate at 2 pi over 3. Notice the y coordinate, let's see, 2 pi over 3 is right up here. Y coordinate ends up being square root 3 over 2. So now once I know what the sine is, it's square root of 3 over 2. Cosecant would just be the reciprocal of that. So the answer here would be 2 over the square root of 3. Just flip that sine answer. Now the last couple deal with inverse trig functions. So if you're going to find the inverse of a trig function, this is where it's specific to its domain. And so if you're going to look up sine inverse, right? Sine inverse is specifically the right half of my unit circle. And we're looking up where on the right half of my unit circle is the y coordinate, square root 2 over 2. And if I look strictly on the right side of the unit circle, it's positive square root 2 over 2 right at the pi over 4 mark. And so my answer is pi over 4. It's a radian measurement. So you're really determining where that happens. When is my coordinate that, right? So the cosine inverse here, that's the top half of the unit circle. That's the domain of cosine inverse. And so cosine, remember, is your x-coordinate. And so where on the top half of my unit circle is the x-coordinate? Positive a half. Well, if I look around the unit circle, it looks like it's right there at the pi over 3 mark. So pi over 3 would be my final answer for letter F. Now the real important thing in calculus is just being able to solve various trig problems. So I know we spent a couple days in pre-calc doing this, but just refreshing your memory on how to solve in various cases. In the first couple ones, notice there's a single trig function left. The part up above, it says we need to solve all the values from 0 to 2 pi. And so that means just everywhere around the unit circle, I'm looking for my answers here. But first, you want to isolate the trig function by itself. If I just rewrote this and said 5x plus 2 equals x, and to solve for x, you would want to get it by itself. So the same situation's true for any trig function. That if I'm going to solve a trig function, what I want to do is try to get it by itself. I'm going to want to maybe collect the signs together on one side. So in this case, by maybe subtracting sine of x to both sides. So now I have 5 sine minus 1 sine gives me 4 sine of x equals, and then if I subtract 2 to the other side, looks like I got to get rid of the 4 in front of sine, so I'd want to divide that to both sides. And now we get this, sine of x equals negative 1/2. And when you're solving this on the unit circle, essentially you're seeing when is my y coordinate negative 1/2 on the unit circle. And so here we're looking for all values around the unit circle, everywhere from 0 to 2 pi. And I think if you look on the unit circle, you'll find that it's negative 1/2 right at that 11 pi over 6 mark, and also it's a negative 1/2 right at the 7 pi over 6 mark. So our two solutions here would be x equals 11 pi over 6 and 7 pi over 6. Those would be my answers for letter A. Notice letter B is very similar. It's a single trig function, so we first want to maybe get rid of it by itself. So let's subtract that cosecant over, 2 of them, to the other side. So now it reads 1 cosecant x equals square root 2. Now remember, when you're looking up cosecant, which is the reciprocal of sine, I guess that's the same as finding when the sine of x equals the reciprocal of this right side, which would be 1 over the square root of 2. And normally you don't see that on the unit circle, but if we rationalize that by multiplying by the square root 2 to top and bottom, we end up getting square root 2 over 2, which we can look up on the unit circle. So when we're solving cosecant equals square root 2, we're really solving when the sine of x equals square root 2 over 2. And that happens at x equals, I think, the 45-degree mark, so at the pi over 4 mark. And it also is true in that second quadrant at that 3 pi over 4 mark. And if you have your unit circle handy, you can check those answers. Now, for the last one, which is a little bit above and beyond type question, it involves a couple trig functions, and notice one of them squared. So the point of this problem is just to refresh your memory about those Pythagorean identities that we talked about in pre-calc. Right? It's true that cosine squared plus sine squared equals 1. That's one identity. Another identity you should know is that tangent squared plus 1 equals secant squared. And then the last one we looked at was cotangent squared plus 1 equals cosecant squared. So notice in this one, if you anytime you have multiple trig functions, the goal is to maybe get it down to one trig function. we can use this top identity to try to replace cosine squared in terms of some sine function. In fact, if I were to solve for cosine squared by simply subtracting sine squared over, cosine squared equals 1 minus sine squared. And that's something that I can then replace in this expression. So if I sub that in for cosine squared, you still have that 2 in front. I'm going to sub that 1 minus sine squared in for cosine, and you still have the minus sine, you still have the minus 1, but now we've gotten it down to a single trig function. And if I'm going to solve this, I might want to first get rid of the parentheses, so let's distribute that 2 through. So I get 2 minus 2 sine squared x minus sine of x minus 1. And then this one, I probably want to get maybe everything, it's equal to 0 right now, but since I'm dealing with a squared function, I may want to use a positive squared, so I'm going to move everything to the right here. Notice I can collect these last two terms too, but if I move everything to the right by adding that sine squared, adding that sine, and then looks like subtracting the 1 over, I get to this. And this is a, let's just say, a little bit harder problem of what you'd expect on the test coming up tomorrow, because this is sort of like a factorable type, where you should be able to factor this into 2 sets of parentheses to be able to solve. Now, in order to do that, an easy way to look at this problem a little differently is instead of writing it as sine of x, let's just write it in terms of x. Let's just rewrite this as 2x squared plus x minus 1, and then just factor that like we do any others. If you do the slide and divide technique, you'll find out that your factors end up being 2x minus 1 and then x plus 1 as factors. So then the 2 solutions from this, right, if we were to solve a quadratic, would be x equals 1/2 and x equals -1. But what did we let x equal originally? We let x equal sine of x. And so once you solve these factorable types, we call these, let's resub that sine of x in for x. And so I guess we're really solving when sine of x is 1/2 and when the sine of x is -1 on the unit circle. And so if you look up at the unit circle, it's going to be positive 1/2 at, well, I think one solution would be at the pi over 6 mark, right, 30 degrees. It's also positive 1/2 at the 5 pi over 6 mark. So we get 2 solutions there. But then this one, when is the y coordinate -1 on the unit circle? And that only happens at 3 pi over 2, right? 270 degrees, the y coordinate's -1. So in this case, we actually have 3 solutions. The last part about trig functions is just kind of knowing some basics about, you know, what these cosine and sine functions, the parent functions, look like, and then really surface level transformations, right? What does that 2 do in front? Well, that affects the height of the wave, the amplitude, right? That negative is going to be a reflection of that function, but then I also have to shift this up 1 unit. So using your transformations, but it's also key to know the parent functions, that if you graph y equals sine of x, just the parent function there, you're really using your unit circle to do this. So if you look at the unit circle, what is the y coordinate at 0? It ends up being 0. What's the y coordinate at pi over 2? Ends up being 1. At pi, it ends up being 0. At 3 pi over 2, it's -1. And so here you kind of get the shape of what sine looks like, roughly. And so if I'm going to graph letter B, right, which has a reflection in front, specifically over the x-axis, and then also I have to shift this up 1 unit. Well, the reflection would just be the mirror image of this, so that's going to look something like this in blue. And then to shift all those key points up 1 unit, I would have my graph. So if I shift this one up 1 unit, this one up 1 unit, this one up 1 unit, and so forth, this would be the graph of negative sine of x plus 1 as a rough sketch. You won't have to necessarily worry about a lot of phase shifts in calculus, anything kind of crazy like that with like phase shifts, and even I'm thinking of like amplitude changes. Some of them, you know, you'll have some reflections here and there. But just know how to graph your basic sine and cosine function. And so if I'm doing the cosine function there, cosine of x cosine of 0 is technically 1, so it starts on the y-axis, but then at 0, or at pi over 2, it's 0. At pi, it becomes -1. So this is all, you're plotting the x coordinates around the unit circle, right? So you get this shape of what cosine is, which looks exactly like sine. The only difference is, sine starts at the origin and has a max point versus cosine starts on a y-intercept. So now if I'm going to graph 2 cosine, the only thing you're doing here is really changing the height of the wave, right? Your height of the wave is not 1 anymore, it's 2. And so that's just going to stretch this function so it looks stretched vertically in the amplitude area. And so anytime you have the height of the wave, you're just going to kind of stretch that a little bit. And this would be the rough shape of what 2 cosine of x would look like. So don't forget to take advantage of the discussion page out there if you run across a problem that you kind of get stuck on. We'll take some time at the beginning of the hour tomorrow to kind of review some of this trig stuff together. Have a great day.